Good morning, everyone. It's a real honor to be here. The last time I spoke to, I'm a computer scientist / electrical engineer by training. And the last time I spoke to a room full of people from civil, and the hazards crowd was maybe 4 years ago at a hurricane conference. So, which was a very exciting experience. So I'm looking forward to interacting with each of you here today. So Jamie invited me to come talk about big data and machine learning. She said, pitch it for engineers, right? So, 25 minutes is hardly, time enough to summarize sort of amazing, things that are happening in the world of machine learning, particularly in deep learning. So I took a slightly different tack. I thought I'd start by giving you what I think are the major challenges in applying all of these wonderful methodologies, technologies to the problems that interest you. All right. So what gives me the authority to talk about that? Well, I've spent the last maybe eight plus years looking at a problem, two problems: wind risk, predicting damage to residential homes because of hurricanes. I come from Houston, so wind interests me deeply. And then, of course, flooding. Flooding is almost a monthly occurrence with rains. And I live in the ground zero of Houston, Meyerland. So this is also of great personal interest to me. So I've spent the last, like I say, 7-8 years on this problem. So I'm going to illustrate all of my points in the context of those problems, and I hope I can connect with some of you in that process. So the perspective I have really is we now have the ability to get huge amounts of data through sensors and through all other ways that we can gather information. My perspective is how can we use all that information and all of the computation that we have to help answer questions that matter to us. So the way I select problems for my own research is, does anyone other than me care about the solution? And this has been a very productive research agenda, and I've worked in a whole bunch of fields. I'll give you a short glimpse of that before I move on to the natural hazards domain. Well, I think the key point is that machine learning is the primary technological enabler for data-driven decision-making. So I think we humans, we've been building decision support systems, algorithms for as long as we've been around. But I think what's new right now is the ability to not just freeze an algorithm, but constantly adapt it with new information that becomes on time. That, I think, is the power of machine learning. Now, I've worked on a large number of projects. I won't go into them. And clearly, this audience does not need a, the message of this slide. Huge, you can't open up even a Wall Street Journal or a New York Times without seeing yet another headline on applications of AI or machine learning to, some relevant social problem. So it's already at the heart of speech recognition. We all have our Alexas and our Siris, and though we may be occasionally frustrated with them, I mean, they do work at a pace that someone like me who started, in the mid-'80s in AI, and I can barely believe that we've come this far. Handwriting recognition, all kinds of financial applications, computer vision, and I'm happy to see there are representatives here, medical diagnostics. It's transformed natural language processing and particularly translation. And in fact, machine learning has permeated literally all of science. I was doing an inventory of, the top 10 Science and Nature, pick out the top 10 discoveries every year. And when I looked up that, 70% of those papers have machine learning as an integral part. So clearly it has helped. But I want to actually have you look at these applications and actually wonder, how can we leverage all of these amazing advances to the work that we all do? What is interesting about all of these highly successful applications? So let's look at translation. It's one of the biggest wins, actually. So, and that has been enabled purely with it's been enabled a lot by data, is collecting side-by-side translations. That is the biggest source of improvement. But you've got to understand that in translation, for the most part,
Get closer there. Yeah, because we have all the people on Zoom.
I'm so sorry if I faded away. I'll try to remain rooted in one spot.
It's hard.
I know, because yes. So you got to understand that all of these applications, you got what happens when the model fails. Okay, a translation error, well, leads to a joke on Google Images. You can see a restaurant somewhere in China called translate server error, right? And no one's the wiser for it, right? Let's look at medical diagnostics. There was a huge splash that Google made when they had their diabetic retinopathy engine, which would read radiology images of eyes with diabetic retinopathy and tell whether or not this was needed medical intervention. Worked at a 98% accuracy on the images that they had trained on. When the FDA required a trial, and it was actually, they ran a clinically approved trial in 3 hospitals, turned out the accuracy of the system dropped to 50%. So there are challenges, is all I'm going to say, and I'm actually going to illustrate what the source of those challenges are, and for you to reflect on what is the relationship between the problems that the methods have been successful for, at so far, and the problems that you and I are working on. But first, a small segue into how I think about machine learning. So in almost all cases, this is the situation. There's some complicated system. It could be understanding how a structure behaves under a wind load, or a whole set of structures behave under earthquakes, whatever your favorite problem is. You observe, obviously you do not have a complete characterization of it. If it's a physical system and you can collect data, observations, you collect that, and that is what this training data business is about. So you observe the inputs and outputs of a very complicated system. You usually bring in a lot of prior knowledge, typically in the form of pre-existing models, the physics that describe how this, or the constraints that this complex system has to obey. Then what I do, I mean, my job is designing these green boxes, the learning algorithms that take this training data. It can come in various forms, and I'm going to describe them briefly on the next slide. Combine them with already pre-existing information to design predictive models. The idea behind building these predictive models is to be able to successfully control this complex system. Because if you understand the I/O mapping of this complex system, you can decide how to actuate it in order to have it do the things that you want to do. And by the way, this is actually a very successful model. Amazon uses it very effectively. The complex system in that case is each of us. And the goal is to make us buy things. Amazon watches us because it has no idea who, it has no idea inside our heads, but it watches us navigate its website, collects training data on us, as well as a lot of other people, and it clusters them. This is unsupervised learning, uses prior knowledge about human behavior and other sorts of things, uses very powerful learning algorithms to build a predictive model that shows us precisely the objects we want to buy. I always joke that Amazon knows what I want for my birthday better than my husband of 31 years. I kid you not. So clearly, in certain fields, these machine learning algorithms are, rocking it. Broadly speaking, so if you take a, 10,000-foot view, the type of machine learning that we do is very much a function of the nature of this training data. And so there are whole communities devoted to understanding and advancing work in these 3 sort of broad areas. In supervised machine learning, the data comes as labeled pairs. So you're given an object and you're given a value or a classification or a label associated with it. Then the job is to determine or find a function that predicts correctly on new objects X. This is very similar to what you did in high school when you did least squares curve fitting. You were given X, Y pairs, so X and Y were an R in the real, and you tried to find a function that captured the relationship between X and Y. So this is just that same problem, but on steroids, because the X can be anything. It can be an image, it can be a whole novel, whatever it is. That's the only difference. Deep learning comes in here, by the way, within this framework, because The usual way of formulating supervised machine learning problems is to represent the object to the machine using features that we believe are important for that problem. So if you have an image, what are the aspects of the image that you think are relevant to it? So for example, if you have a radiology image with lesions, we will give it features, higher level features than just the pixels alone that will allow a machine to infer the relationship between the extracted features and the classification. What makes deep learning so exciting is that it has eliminated that human component of feature extraction. We no longer need expert radiologists to sit there and say, I count the density of these types of features and these are the properties I use. You don't need that anymore. We can do end-to-end solutions, okay? So you have to ask yourself, is my problem one in which I can do an end-to-end solution where I throw raw data into the machine with an associated label or a value and then build a function that's going to predict the value or the class directly from the object. In unsupervised machine learning, you're just given objects or vectors, usually vectorized. And you have to characterize the density function or the distribution. So you can put it in many different ways, find clusters, find latent variables, etc. So here, notice there are no labels. You're just given a boatload of data and you're asked to characterize it in some interesting way. Usually, this unsupervised machine learning, like for example, k-means clustering or principal components analysis or their nonlinear variants, are used as a precursor step before doing supervised learning because it sanitizes the data in some interesting ways and allows you to find patterns much more easily. Okay, the final kind of learning, which are important only when you're trying to learn policies over time by interacting with an unknown environment. So this is the magic behind AlphaGo. So AlphaGo is actually a very interesting reinforcement learning algorithm, deep reinforcement learning algorithm. So this, I hope, gives you an idea of the different types of learning that are out there. So why do we need machine learning at all? What is, when, you might think that being a person in machine learning, I would say, it's always the answer. No matter what your question, the answer is use machine learning. And actually, I'm here to tell you that's not the case. So here are 3 minimal conditions that must be satisfied before you jump into machine learning as a possible method. If you have a nice analytical model already for your complex system, there are a plethora of other techniques for approximating them and simplifying them. You don't need machine learning. But when you don't have that complete analytical model, do consider machine learning because you might be able to infer that model by observing inputs, outputs from a complex system. If the requirements and the environments change rapidly and new sources of information come online, and therefore no fixed decision rule works for all time and space. So this is the situation, for example, in elevator design. Have you always wondered why, when you enter an older building and it's a multi-story building, the elevators are, excruciatingly inefficient? The reason for that is that the decision rule for handling elevator calls is built according to projected traffic flow when the building was built. But building use changes over time, and elevators do not learn those patterns. If instead we had elevators, by the way, the elevators do know the traffic patterns. They can infer it because for safety reasons, they can sense the load. They can sense the load every time. So, an adaptive elevator system would not age out like that. So if you have a problem where you think new sources of information are going to come online, and so the decision criteria are not going to be fixed for all time, do consider machine learning. And finally, problems for which there is tremendous individual variability, right? So if I build a flooding model for Houston, can I just take that model and transport it to, I don't know, some Midwestern city where, say, the Mississippi flows? Probably not, right? So I will have to customize it. Does it mean that we are going to have to build solutions like for each location? So what you want to do is to build a core structural model and then customize it with machine learning for each different location. So these are the types of ways in which machine learning or situations where you might want to consider machine learning. The real advantage of using machine learning, of course, is instead of having human engineers model these complicated systems, and they always need to make very strong assumptions to make models tractable, you can actually learn, hopefully, with sufficiently powerful representational mechanisms, directly the relationship between inputs and outputs using supervised machine learning. The result will be a more robust system that adapts to new information continuously without being reprogrammed. At least that's the promise. There are a lot of fundamental questions in designing a machine learning system. And many of them the field does not have very good answers for. What data should be gathered to make predictions? More importantly, what should be predicted at all is not something that we can really help you with. This is where the domain science comes into play. I have made errors in picking my prediction target and wasted years working on a prediction problem that was inherently undoable, backed off and chosen a different prediction target. What class of models do you build from observed data and prior knowledge? This is the model selection problem. Notice that we're not yet talking about learning algorithms at all. This is just setting up the learning problem. What should be predicted? What data is needed to predict that? And then what is the form of that final answer, at least in terms of what is its representational complexity? This is the most important question for which we have no general answer. This is why the diabetic retinopathy experiment failed. The best methods we have for validating a good predictive model, those methods do not scale. So when we take something that has worked in the lab and we transition it into a real working environment, things may not work as expected. So I think there's a lot that needs to come from by collaboration between people in machine learning and people in the domain sciences, because I think there are many innovative approaches there that use domain science as the anchor for validating models. Now comes the thing that is my day job, which is making algorithms for actually learning a family of models from data that we have selected and for the prediction problem that we have carefully chosen, right? How do you scale them to work on large data sets? That's sort of the most of where machine learning research is currently engaged. But I think what we can get from domain scientists is how to solve the first three problems, because the success of a machine learning project very much is a function of how you answer those first three questions. There are even more fundamental questions. How do you incorporate prior knowledge? It's a myth that we can do end-to-end completely data-driven solutions, okay? There are very few problems that fit that bill. Besides, why would you have to rederive F equal to MA from scratch from data? I mean, you know that, use it and leverage the data for something else. Incorporating learned structures into larger systems. The machine learning is never the full solution. It's always part of a solution. How you engineer that, taking what the models you already have and then having the tunable components and how do you make them work together? That's hard. How do you make learning algorithms practical? And particularly with limited resources. There's a huge amount of work being done right now on how you run, these skin lesion detectors on an iPhone. Well, that is power limited. There are so many limitations. How do you design algorithms? You can't just say, well, we'll make a call to our, to the computers right in the back here, or maybe use the cloud. I mean, you may not be in a situation where you can transport the problem to the cloud. Finally, how do you trade off accuracy, sample size, and hypothesis complexity? So I have 3 minutes, and I've barely gotten into what I wanted to say. So I'll be really quick. All right. So one line, learning algorithms are optimization problems. So this is why we need the help of all our friends in applied mathematics. The perception of machine learning is that you pour big data into this nice funnel, you hand it off to your collaborator in machine learning, and then the next day they show up with nice, useful models. Okay. No. Okay, sorry. Why? As a machine learning scientist, I would like this vision to be true, but we're not there yet, okay? Because of all the fundamental problems, what should be predicted, what data should be gathered, et cetera, et cetera. We don't know the answers to that. Often, particularly with my medical collaborators, I will get data and they'll say, yeah, I've got 5 patients. Now tell me, and I go, 5 patients? I can't build a model on 5 patients. Can you draw a quadratic on 5 points on the plane? You can't. Now you want me to have a whole theory of T-cell signaling from 5 points? So yeah, these are issues. So, in the interest of time, I'll tell you what I have learned. I have worked on a huge range of problems, including natural hazards, medical problems in understanding Twitter data. So I have a research program where we look at tracking political events on Twitter to try to understand. So the latest one was on gun control. How does the American public really feel about gun control? Stuff like that. So the algorithms I use for all of them, they are the very same algorithms, but a considerable amount of ingenuity is needed to map those algorithms into these application domains. Here's what I've learned after 2 decades of working in this area. The most difficult part of the problem is determining what is worth predicting. I can't emphasize this, hard enough. Machine learning can be used to debug complex engineering systems. And if Jamie is kind, I will show you just one example. And model ensembling is critical for handling decision space heterogeneity. See, it's very unlikely that one method or one model will solve your problem. I have found great success by actually ensembling or putting together models. In performing predictions under uncertainty, which is almost always, it's worthwhile to gather information over time and update models over time. So I always prefer to work in a decision-making context where information just comes in over time. That's much better than getting a whole pot of data in the beginning. Somehow that temporal information is crucial for resolving uncertainties. Finally, if you want to build a robust machine learning solution, you have to integrate multiple sources of information at varying spatial and temporal scales. So what I'm going to talk about is work that I've done with my colleagues, Leonardo, Duenas Osorio, and Bob Stein, Rick Wilson, who are 2 political scientists. Leonardo is a civil engineer. I would just briefly talk about wind risk and approaches for predicting wind risk. Well, you can use physics-based models, and some excellent models out there that are built into widely used systems such as HAZUS MH4. And then there are data-driven models. I'm going to show you the challenges in building data-driven models for this particular problem. Well, I won't belabor this. You guys know all this. So I will show you how well the model performed, the FEMA model, on Hurricane Ike. So Hurricane Ike, we were very lucky. We got damage assessments on 800,000 homes in Harris County. And so we got this work published. I just want to show you that this was the prediction by the HAZUS MH4 model for the predicted wind fields of Ike. And this was the observed damage. So I put them side by side at a census level. So you can see that there are some difficulties with the model, all right? So clearly, there's a lot more damage out in this region. I want you to notice that, which is not captured by the FEMA model. So why? What is wrong? Well, at the census tract level, 59.24% of the tracts were predicted correctly for damage. And at the 1 kilometer square block level, the accuracy dropped to about 51%. So we did error analysis using machine learning. What is the cause of the discrepancy between observation and prediction? What are the characteristics of the tracts and blocks where the fragility curve-based model makes errors? So basically, we got a whole bunch of explanatory variables. This took us a lot of time. And we basically wanted to predict where are the errors. So lots of explanatory variables. And you can see these factors are not taken into account. What is the land value? What's the building value? You can notice that the damage was high in areas where the building value was low, which are old, which haven't been remodeled, which are of low quality. I know. So we built the model, and I'll cut to the chase. Basically, machine learning helped us understand what new parameters will have to be added in order to make the HAZUS MH4 model really much more predictive. So we even got detailed explanations of exactly why the model failed at particular tracks, at particular blocks. This is what machine learning can do for you. For models built directly from data, so why, we have 800,000 homes, why not build the model directly from data? Now here was the question, what should the prediction target be? Risk at home level, at block level, at track level? How do you establish the quality of the model? So we used the same explanatory variables. We fed the 800,000 homes and basically built a decision function. And I'll stop on a high note here, but because what comes is a failure and then a resurrection. Yeah, so it works very, very well. So we in fact, so well, that we actually fielded for 5 years a storm risk calculator for the city of Houston, where anybody with a home in Houston could actually type in their address and get risk of wind. So lots of stuff. I also work on flooding, and maybe I should cut to the chase and give you two, if I can leave you with 2 images. Our latest way of predicting flooding, inland flooding, use all of this information together with new sensor networks that measure the level of water on the road and basically give you this level of detail so that when you pull up your map on your iPhone and want to get from point A to point B, you will know the level, whether your car will get through them or not. So anyway, thank you for listening to me. And if you have questions, come ask me.